No need to look at it. It's like talking. Read closer. It's closer. The board is visible.
Yeah, it's visible. Hello everyone. Welcome to our channel. Today we are going to solve or talk about the relativity thing, proper length, proper time, improper length, improper time, in moving frame and in rest frame. We'll discuss about these topics, and I already have made some videos on these things. One video is on muons, traveling muon, and another video is on twin paradox. You can check these videos in my YouTube channel. They are already there. It has been uploaded a couple of weeks earlier. Check it now. This time I'm extending the same problem, the twin paradox problem, and I will solve it up to a next further step. See, earlier when the video that I have uploaded in my channel, in that video I have also solved the twin paradox, but just the time dilation part. Here I will take some of the length contraction part too in the same question. Now the question was, I am writing it here. The question was, there were two twins. See, suppose this is the earth frame and one twin is here on earth, and another twin who moved on a spaceship. Suppose this is a spaceship.
One viewer is on the live. I think he'll press down.
Suppose this is a spaceship, and the twin who moved from the earth point to a star X.
Right, the topic is.
Wait. Yeah, the topic is the twin paradox. And it's a question. The longer video is already on my channel. See, it's not visible.
Yeah, it's visible. There is one person there.
See, the topic was both the twins on earth, they were on their 21st birthday. One of the twin tell that the brother, he stayed on the earth, and another twin, the sister, she moves in the spaceship. She sat on a spaceship and she moved from earth to a star X. After reaching the star X, she took another spaceship which is traveling in opposite direction, and then she moved from the star X back to the earth. So after reuniting, it has been seen.
Read the comments.
What is the comment? Wait, let me check.
Yes.
Does it happen? Yeah, I'm going to explain all the details. See, you question, does this happen only in the inertial frame of reference? No, I'm answering. There's a comment in my channel that does this happen only in the inertial frame of reference? Here comes the extra analysis. See, if we solve this twin paradox from the special relativity point of view, then we can simply take this as the inertial frame, then this moving spaceship, it will become a non-inertial frame. But in general relativistic theory, as we all know, the earth is also not in completely rest, and generally in realistic case, earth is not an inertial frame, completely inertial frame. It has it is moving on its axis, and the earth is rotating on its axis, and the the rotating earth is also moving in a elliptical axis about the center of sun, so it has some dependent it is not in completely inertial frame, it is also a non-inertial frame. And in general relativity, this has been taken in account. Even in non-inertial frame too, this happens, but we just need to apply the relativistic equations. It has been enhanced, little bit enhanced for the general relativistic case. That's what I'm going to tell you, how to solve this in relativistic, in a special relativity formula thing, and how to analyze in general. I'm just explaining why. I'm just, see, it's a theoretical thing and I have to get some time to explain. I thank you so much for all to joining me on live, and I'm just explaining it, how it happens. See, there are questions coming in my live. Okay, see, first let me solve it from the special relativity point of view, then I will analyze it on the general relativistic point of view, how we used to apply things. And see, check it, this star X is not visible. Wait, write it, the star X here is still not visible. It is still not visible. Tilt it a little bit. Wait. Yeah, now it's visible, the star X here. First solve it, I'm solving it. Wait, and just stay, I'm explaining it now. See, the question was earlier, this twin stays on Earth, suppose it's the brother and the sister, she moved in a spaceship up to a star X. She jumped from this spaceship to this spaceship and returned back to Earth. Now, the speed earlier of this spaceship was 4/5c, or you can take it as 0.8c, it's the same thing. And when she reached up to this star and she turned back, this spaceship also has same speed, only in the opposite direction to reach on the Earth. It again has same speed. Now, in a special relativity, how we'll solve it? Is this? Yeah, this is visible. See, as we all know, the general formula of time dilation, we write it, T is equals to gamma T naught, where this T naught is the proper time. Now, first understand what is a proper time and how we'll apply it. See, in general language or in a special relativity as we use it, as we solve it, the proper time is the time which is measured, or you can say that a time viewed by the clock of the observer who doesn't feel any motion, right? So here in this example, the proper time will be the time which is with the moving, the twin who sat in the spaceship and moved. The time measured from her clock will be the proper time in her frame. Remember always, wherever we measure the distance or time, we need to assign the reference frame. Without reference frame, we generally cannot say that this is proper time and this is improper time. The time measured by this twin on her watch, the watch is also moving with the twin with the same speed in the spaceship, so that time is the proper time in her frame. And this twin who stayed there, she will measure the different time than this twin of the same event. Wait, I'm getting another comment too. Dear ma'am, I have a question. We know that our universe is expanding continuously. Yeah, this is a better question. Bhaiya, check the comment. It's enlarged it.
No, it's already there.
Up to they left it here. Okay. See, I got a question that we know that our inverse is expanding continuously, redshift in a spectrum. Yeah, this is the thing that will come up in the general relativity analysis. The distance is not changing in any isolated system like our solar system. No, distance, see, the measurement of distance, it also changes. It depends on the reference frame. I'm going to calculate this part too also in it, like the distance of Earth and the x star x as measured by an observer on Earth, this twin, the brother, and the same distance that will be measured by the sister will come out different. The length contraction says us that thing. The length, the time, everything in relativistic, it depends on the observer. It is not absolute. You cannot say, as in our general language, we say the distance from this point to that point, maybe from our house to our school or some other place, we take it as a straight line. It's a fixed distance. But when we think in outer space view or in relativistic view, this is not a straight line. It's not a fixed distance. It depends on the observer as we all move. Yes, see, I got another question. Is it somehow related to dark energy? It's a very good question. See, in outer space, we have very, very less knowledge. Everything is theoretically, or you can say it's not theoretically, it's in mathematically. And the equations haven't been completely designed, or we haven't got the equations yet completely. So there are a lot of things which is only in the analytical form, and everything can be related to every other thing. We say the dark matter and dark energy, we named it dark because we don't know anything about it. It's in dark, that's why we name it dark matter and dark energy. So yes, it could be possible that the distance which happens to be measured different by using Lorentz length contraction, it could be possible that the difference in measurements of length or time by the different observer could be related by the dark matter of the inverse thing or the dark energy thing, because we all know the time is also not absolute thing, and measurement of an event is measured, whose call is this? An event is measured the time in one frame, and same event as observed by the other observer in some other frame could have different time. So if we think in our daily lives, then we just got confused. We seems like, see, check at any happening event, like it passed 5 minutes in our clock, it happened in our frame. But if someone sees us from moon, as we have reached our moon and up to the Mars, if someone sees us from there, they could measure some different time than these 5 minutes. So the happening of these events, yes, it could be related to the dark energy or the dark matter thing. I haven't read that much yet, but I will read it and I will come up with another video about these things. Right now I am just solving this question, and I will tell you in the analysis that how it happens. How it happens, the time dilation and the length contraction, and how it changes our perspective, our view, how it confuses us that in a space it is not a straight line. The distance from this point to this point, it's not fixed. See, solve it now. No, I was explaining the proper time, and in this formula you could have seen in the books, like this is written in delta form, the time period, and this is also written in delta form. The reason of writing this in delta form is because, as we say, the time is not absolute. We generally take the interval. Very small for very small intervals, we can take this as t and this as t naught. And it really doesn't affect in problem solving if you take it delta t or simply t or delta t naught or simply delta t naught. You can take anything, whatever you like. See, I was explaining the proper time. The discussion, the analysis of proper time and proper length is very necessary. And lot of students, lot of people confused in it, gets confused in it. I'm getting another comment. Can you explain about the true definition of energy, mass? Yes, I will definitely explain the definition of energy and mass in some other video. Yeah, and it's very, I think you are a very curious person and you have very deep understanding of the inverse and basic things which need extra analysis and extra thinking. The generally book does not define what is energy, what is mass. They give the general definitions weight by gravity, acceleration, this is one. But no, that is not the real explanation. And you could also come up, think, whatever you want to think on these topics. These are the topics which need the further research, further thinking. And the fresh minds, the minds that are very fresh, who doesn't think like the book, that is very necessary in this field. All of you are welcome to think on it, and whatever you think, just make the video or connect people like those who think out of the box. This is very necessary in thinking in these higher topics, that you should think out of the box, not the definitions in book. And whatever you think, see, for the research topics, it's very necessary that you don't feel like we need to think it so true, means a right thing. For coming to any right conclusion, we need to do it. And whatever comes in your mind, it could be wrong, the analysis could be wrong. But you need to think of, you don't think that oh, when I get right, then I'm going to prove this theory. No, these are the steps. As in reading the books, the questions you could have seen in quantum physics. First, for example, take the quantum physics, like first Thomson made a model of atom, then Rutherford came, then Niels Bohr came, and it's still not fixed. We are still discussing, we are still developing theories on it. So it's very necessary that you could think out of the box, and it's also quite common that your thinking may not be complete in all things, or it's not right 100%, but think up to it, and whatever you find, whatever you think, put some analysis, like in a physicist way, of course. You don't need to do what can you say, like you can think like that extremely, who doesn't understand physics, think like a physics understanding person and make the videos on it, put your thoughts in world's view. It's very necessary. See, now let's solve the question. I was discussing the proper time, and I told you the proper time of this twin which is traveling will be the time noted on his watch, maybe on his wrist, on the spaceship, and the time calculated by the Earth of this event, this spaceship moving from here to here, will be improper time. This is the key thing. In a special relativity, we think that this twin is in rest. It's completely in rest in Earth's frame. That's why we take it as an inertial frame, and we take this as a non-inertial frame, because it starts from here, moved to here, and then turned back. If it's kept moving on a straight velocity, then it could be also taken as inertial frame. But that doesn't happen. It reached here, turned back to another spaceship, and it means it felt acceleration. That's why we take it as non-inertial frame. And the time noted as the non-inertial frame in the time which is measured or which is observed in the moving frame. But the clock should also be moving in that place. The clock should also be kept in that place. That time will be this T naught in this formula. So if you have any confusion, you can ask. Yeah, you can ask me. See here. And earlier the question was that they two departed on their 21st birthday. This is a question of the Griffiths book, problem number 12.16, the twin paradox revisited. So for the detail, the question was too long, it took off half of the board.
Same member, and chant the name of the channel who is messaging.
See,
he told you that make a video of energy and mass. Tell him the next video and make a
Yeah, I have already told him that I will make the next video on energy and mass in some other video, and the name of your channel who is commenting is @Quantum Mathematics 777 with no space. See, now let me solve the question. The problem was that at 21st birthday, they two she departed, he stayed, and she reached up to star X, entered in the return spaceship and moved back to Earth. Now after reuniting, the time elapsed on her reference frame, on the spaceship frame, the time elapsed is she felt it that she reached at 39th birthday. After reuniting, this twin, the sister, was on 39th birthday. Means the time elapsed on this frame is 39 minus 21 equals to 18 years. So in her frame, in the spaceship's frame, the time elapsed in this whole process from starting here to reaching at star X and from coming back to Earth, the time elapsed was 18 years, and that was in her frame. Then what would be the time in the twin who stayed on the Earth, the brother's frame? We'll simply put the formula here. See, V is equals to this, so gamma will be, and T naught is 18 years. Putting the value of V, you will get the value of gamma as 5/3. Calculate it here. 1 by root under 4/5 cc whole square. This cancel, this becomes 416 and this becomes 25. 25 minus 16 becomes 9, and since it's in root, it will become 1 by 9 by 25 under root, and that will make it 5/3. This 25 goes upstairs here, and coming out of the root, this will be 5 and this will be 3. So gamma will be 5/3. Put the value here, 5/3 into 18 years, 3 6 18, and this becomes 6 5 30 years. Now wipe it up. See, there's a marriage procession is going. I get another measuring the time in this twin paradox. Which clock is considered the reference clock? The clock on Earth or the clock? No, wait. I'm telling you. See, we can solve this problem in both ways. We just have to take the proper time and improper time in case. We can solve it in both ways. Here I have solved it in this way, that see, in this formula I have already explained the proper time will be the time measured as rest. The clock will be at rest with the moving system, the system which is in motion, which is not in rest. So this will be the proper time. And we can solve this same thing if we take the reference frame as the Earth frame, then gamma will be same, but we'll have to take on the respective point of view of the twin who stays on Earth. In problem, we have given that the sister who moved from here to a spaceship returns on her 39th birthday. This was given in the problem. That's why I took this formula. If it was given, we can solve it in another way too, as I'm here solving it. Wait. From this formula, we get the twin who stayed at Earth. This time, the time which elapsed 18 years in her frame will be the 30 years in his frame. Means the event was same. She started on a spaceship, reached the star X and came back to Earth. It was also viewed by her brother on Earth. He saw her sitting on a spaceship, reaching on star X and from there coming back. The same event was measured or was observed 18 years in her reference frame. And this was given in the problem that she reunited on her 39th birthday. And this same event was measured 30 years in his reference frame. Now, if we have been given, see, I am calculating it in the other view too, other point of view. If we have been given in the question that the twin who stays on Earth was experiencing his 51st birthday. Yeah, I'm analyzing this part. The twin who stays on Earth have birthday, in this case, the twin on Earth, Yani means brother, will be 21st plus 30 years is equals to 51 years. See. Now, since we have given this, the hard timing, so we solved it in this way. If in the question we have been given that after reuniting, the brother was of 51 years, then how much time elapsed in the sister's frame? If this were the problem, then we would have taken this time as the improper time, because here here this twin was in rest, in the Earth frame it was rest, as we think in the special relativity, this is inertial frame and this is non-inertial frame. So the proper time remains fixed. As I have told you earlier, the clock which is in non-inertial frame, which is moving, but it is at rest in that moving frame. This clock should be supposed to be here on the spaceship. The time measured on this clock will be taken as proper time in this formula, in the special relativity formula. So if we have been given that the brother has age 51 years, then we would have used this 51 years here. Then we would have used this 51 years here. Gamma will be again 5/3, and then we will have find this time t naught, because we didn't know the time elapsed in that frame. And then it again came with the same calculation. The time elapsed here will be 30 years, because at 21st birthday he moved. We need to calculate these times as 51 minus 21 equals to 30 years. So if we have put this, then it's the same thing. T naught came up 18 years. In a special relativity, we solve it like this. But the same thing, as you were discussing here, I got your comment that which clock is considered the reference frame, the clock on Earth or the clock in space, outside the Earth's gravity. Yeah. Now, in a special relativity, we solve it like this, that this is proper time, the clock which is in moving frame, but which is in rest in moving frame. It's not moving in this frame. It's rest with the spaceship. We take this the proper time. But in a special relativity, but in general relativity, yes, your analysis is right. It's always our choice. We can take any as our reference frame. We can take this also our reference frame. We can take this also our reference frame, and then we calculate it. And in general relativity, it happens. The result, the equation is not exactly this. I have in my copy the equation which is used in general relativity. See, I'm going to write it. See, the same formula which was T equals to gamma T naught in a special relativity, this same formula becomes this in general relativity. See, there has been some derivations. I'm not going to write them now. The resultant formula is, see this, in general relativity it becomes with variable speed. Earlier it was T is equals to gamma T naught. Putting the value of gamma is 1 by 1 minus V square by C square T naught. Now move this to here, then T naught becomes root under 1 minus V square by C square and T. This is again the proper time. This was for the constant velocity, but as we know, the velocity in space does not remain constant, because it is, not the straight line. I'm coming on the analysis. In general relativity, this term becomes variable, and we represent it d tau. As we know in differential or integral calculus, in calculus form, this becomes d tau. Is it visible? Let me write it here. See, the d tau becomes, this quantity remains 1 minus V square by C square, and an additional quantity that comes in it is 2 phi by C square. And this T remains this T. Let me wipe it. Read the comments. What are the extra? Are there any extra comment? Okay.
It's 34:55. We can wind up after 5 minutes explaining this.
Let it be. See.
Don't go so long until we get enough.
D tau is C. In general relativity, we solve this thing, and here this also becomes the variable term. Now, why we use variable term in general relativity? See, as we know, let me tell me what is the phi. Phi is Newtonian gravitational potential, and phi has a value minus gm by r. People, if you are familiar with the gravitational chapter, then you can understand this is the Newtonian gravitational potential, gm by r, but this is the gravitational constant, this is mass of the planet, and this is radius of the planet which we are talking in. See, d tau is this. And in general relativity, this same analysis will be solved on this equation. And why we took this, the variable time here in both frames, not the constant form, because the velocity may come in, the velocity has a lot of chance not to be constant if we take in detail the perspective of moving of this, the spaceship which is moving. Here we have solved the problem on the analysis that the spaceship moved on a straight line from here to here with constant velocity and return. But we know that in space, generally when someone travels from Earth, it does not move on a straight line. So we could not be able to solve this on the space. Oh, the light. We have a power cut. It's completely dark in between the live. Oh.
Tell them that I'm going to win.
Yeah, see, it's a complete power cut here right now in my area, and it has been dark. Check out, is the emergency light working?
Afterward, wind it.
Okay, wait, let me wind it. It's summer, you can see as I'm too much sweating. See, I'll come up with another live and another video, the analysis of this. Right now I'm trying to wind up in some, see.
This man is constant in the life.
Yeah.
Tell him thanks for watching.
You are constant in the live, and thank you so much for being constant in this live on my analysis. And I'll try to make the videos as you told me on energy, mass. I haven't read the dark energy and dark matter theories yet, but yes, and I urge you to make videos too. Whatever your thinking is, whatever your analysis is, make the video on it. Okay? I'll also love it to watch your videos on these theories. Since you are asking so deep questions, I'm sure that you also have better knowledge on these topics. Come up with the videos. See, as we know, in space, the spherical universe at the you know what, the accepted shape of universe is a spherical, and on a sphere, if a point moves from one point to other point, it is constantly in helical motion. I will come in detail in another video. So in space, in general relativity, when we take all these things in account, then we use this variable thing, and then this velocity will also have a variable time variable function, and then it become in the integral form. The integration, as we know, it's a quite tough thing, very tough thing, and space integrations are, I think, the most toughest thing. And then this equation and this calculation will be too lengthy and astrophysicist thing. I'm not going there now. I'm just analyzing you that in general relativity we use this equation, and for general relativity it's always our choice. We can always choose which reference frame we are taking, and this is true in special relativity, which is the most realistic explanation of things in space. The special relativity is only on theoretical thing. We make assumptions on it to ease the problem. But in general relativity, when we take everything in account, it comes in general relativity, and all the space astrophysics calculations are calculated on general relativistic point of view. So it's always on the observer which frame of reference you can choose. Just apply the formulas quite well, understanding it. The frame of reference is independent of the choice. We can always choose whatever the frame of reference is, but the proper time applying the special relativity, you apply it as I said, the clock which is moving with the thing, with the spaceship, and it's in rest in the spaceship. Imagine that you are sitting on that spaceship, wearing a clock, and the time measured on your clock will be the proper time. It's for special relativistic things. For general relativity, you can take both the things in analysis and analyze it. Okay, I will come up in another live. The light haven't arrived, the power cut is not resolved yet, and I will come up. Yeah, thank you so much for viewing this. I will come up in another video. I'll make the video or maybe another live in the same time in next Sunday, and then I'll try to analyze this and the point of general relativity. Okay, thank you so much for watching it and constantly being in live, and I request you to make the videos. Whatever thought comes in your mind, please express it, make the video, and I love to see your videos. Thanks for watching. Okay. कहीं लाइन रहते थे